Cool. So I'm Ben. I'm one of the founding engineers at Galileo. And I thought it would be nice because data-centric AI has kind of become a really popular term in 2022 and now 2023. People are talking about it a lot. And because this is just like the first session in this series, I thought it'd be a useful time to kind of talk about what at least data-centric AI means to me and to people at Galileo, and how we're thinking about it, and some things that you can look for and things that you can do today to kind of move your model development from a very model-centric workflow to a data-centric workflow. So at a really, really high level, the highest thing, when you think about machine learning or AI, it's obviously your model code, everything you're doing about the architecture of your model and your data. And so in a typical model development lifecycle, you get your data, you maybe clean your data, you pre-process your data, and then you begin hyperparameter tuning your model. You look at different model architectures, you look at different modeling types. Generally, you're tracking the hyperparameters, you're tracking the losses, and you're kind of continuously changing and tuning those types of things to best fit the data that you have available. But in data-centric AI, we sort of try to change the paradigm of what you're looking to do. So instead of trying to fit a model to the data that you already have or to the data that you presume maps to the problem you're trying to solve, data-centric AI says, well, there's a lot of assumptions today, and there's a lot of really powerful foundational models today. And you can almost operate under the assumption that if you have a data set that represents the problem that you're trying to solve well, you can almost take an off-the-shelf model, fine-tune it to the data set that you have, and you'll probably get really good performance. And so the question becomes less of which model architecture should I pick, which hyperparameters should I choose. You can kind of get, for example, a lot of really powerful models from Hugging Face. The question now becomes, does the data that I have represent the problem that I want to solve? What am I actually trying to do? And does my data represent that issue? And so one way to think about that in a really, really high level simplistic way is to say you might have some data where the decision boundaries really aren't clear. These are really fake examples from scikit-learn, for example. But on the left side, you might fit a model, you might fit some really deep neural network to all of this data, and you might come out with some high level summary statistic, and you might say, well, I've modeled the data. My F1 score is 0.85 and it looks reasonable on the validation and test set. I'm done, like I'm good, we're good to go, especially in the unstructured data world where you're working with images or text, things like that. But in a data-centric approach, you might look at, for example, embeddings, and you might color them by different metadata or different characteristics that you have. And you might say, well, my model has kind of built some line around this data, but the data clearly isn't representative of the full problem. I clearly don't have good labels and good semantics to represent what I'm trying to solve. In fact, I need to go back to the drawing board. I need to get more data. I need to fix problematic data. And I really need to stay there and iterate there until I can properly represent what I'm trying to solve. And so what this means in practice often is a number of different things, but the highest level idea here is that summary statistics can in many cases be pretty problematic and pretty harmful. And this is just one example, and we'll look in more detail in a minute at this example live. But summary statistics will tell you overall across all of your data points, how is your model doing? And you might have, for example, a 0.83 F1, and maybe you were aiming for a 0.8 for some use case. And you might see a 0.83 and you might think, well, that's like really good. I've gotten past my threshold. I'm ready to go. But the problem with summary statistics is they don't tell you where cohorts of data are troubling your model. You may overall be fine. Most of your data might be easy, but you might have some slices of data that are hidden, that you don't have a lot of representation for, and that are really throwing off your model. And if any drift, for example, occurs in production and you get more of those kinds of samples, you might end up in a really bad place. So this is an example of seeing a real model with a 0.83 F1. But if you actually investigate the embeddings and you look at some of the sections, you might find some really bad problematic data where your model is actually performing terribly. It has no idea what's going on. It's kind of cut off here, but you can see your ground truth is all over the place. Your labels are clearly incorrect. Maybe you don't even have a label that represents this type of data. You might investigate further in this case, and we'll look at this live. All these samples were just empty. And maybe you're building a chatbot model or something like that, and you're just getting a lot of blank messages or spaces. And if you don't have, for example, a label to categorize this is a really simple case, you might just not be able to classify these. And the more you get, the worse your model will perform over time. And so just looking at summary statistics, which is sort of what you try to optimize for in a quote model-centric approach, might not be enough, or often isn't enough, and can be really harmful in these kinds of ways. There's a number of other slices that you might want to look for in the real world. Another really prevalent issue that you have to look for and take care for is data bias. So data bias occurs. A lot of people understand the term class imbalance. That's a common term, and people are pretty good at this point at balancing samples across their data set to make sure all classes have equal representation. But there's another issue that is kind of under the hood there, which is data imbalance or data bias. And while class imbalance talks about the classes across your data set, data imbalance talks about within a particular class, what cohorts of representation may be lacking or maybe overblown. So for example, this is some data that I generated using ChatGPT. It's just a bunch of cover letters for various jobs. In this case, it's computer science and nursing jobs. Just a bunch of like pretty long form text inputs, multiple paragraphs, and they're just people trying to apply for jobs. And it states their name, their gender, and the job that they're applying for, and then their credentials. And you might look at this data set, and we'll look at this screen a little bit in a minute live as well. And you might look at this and you might say, okay, well, there's clearly some great separation between my two classes in the embedding space. Clearly the computer science degrees are all over here and the nurses are all over here. There's no problem. Like, let's get to modeling. This model understands the problem. The issue, though, is in this case, the gender metadata category is completely one-to-one correlated with the job description category. So all of my resumes and cover letters here for computer science were males, and all of my cover letters and resumes for nursing were females. And obviously that's really problematic. What happened here is you have massive, obviously fake data bias, and none of your computer science resumes have any women, and none of your nurses have any males. And so the problem with this in production is that you might think that your model is really well separating based on the semantics, for example, of this cover letter, but in reality, it might just be fixating on the name of the person or the gender of the person in their cover letter. And then when you go to production and you look at your predictions, you may have a prediction that is very clearly a computer science degree, but because the name and the gender in here is female, the model totally screws it up, predicts the wrong thing, and you may have never even known that you have these types of biases in your system. And so when you're dealing with these kinds of issues, data bias, data imbalance, metadata is a key factor to include in your samples, especially in unstructured data. You shouldn't just be, for example, making predictions over images or over text. You should be including as much metadata as you have, coloring your embedding, slicing your data by those metadata fields, and seeing how the model performs differently across those different fields, and whether that representation is actually distributed across all of your classes. So there are some really common issues to look out for. These two we just talked about, which would be garbage and noisy data. A really good way to look at that is with your model's embeddings and also semantic data embeddings. Looking through the embeddings, looking for very light or sparse clusters, coloring by metadata, things like that. And similarly with data bias, metadata inspection is hugely important. There's obviously many other components to metadata that you can include. It could be the pipeline that you ran to generate those samples, or the database table or database schema that it came from, or the labeler that actually, annotator that actually annotated those samples. Having all of those things in there gives you so much more visibility into where your model is performing problematic. There are two other really quick issues that I'm going to go through, but I'll also leave some resources for other talks that have gone in more detail. Another really common issue in a lot of data sets that have been been very common, have been shown more and more in the last few months, have been mislabeled data. So a lot of data sets today, have hundreds or thousands or millions of samples, and a bunch of those samples in the data set are actually completely mislabeled. This is the ImageNet data set, and you can see here all these given labels are just obviously incorrect. And the actual label was just something completely different, or in this case, very similar and we'll talk about that in a second. And it's really important to find these samples, to mitigate these samples, to relabel them, because really what they're doing is just confusing your model. And so really effective ways to deal with that are labeler management. So having multiple annotators, for example, go through all of your samples, and then, for example, coloring your embeddings by each different annotator, looking for agreement, disagreement, things like that. And then there's also tools that kind of handle this for you. Galileo is one of them. CleanLab is another. You can kind of pass in your data, and all the algorithms that have been come out in research papers recently are used here to kind of surface those samples really quickly. Another one that's pretty similar to mislabeled could be class overlap. So it could lead to a lot of mislabeled samples, but this is again from ImageNet. There are a bunch of samples here. And for each of these, it's not really clear which label it is. So if, in this data set, cowboy hat and cowboy boots are both labels in the data set, it's not clear which one you should be choosing from these images or any of these really. And many of the same techniques apply to deal with overlap. One unique piece is that you could turn it into a multi-label problem. So your model can predict both of the classes, or all 3 or 4 or 5 of the classes. But otherwise, you could be merging classes. Maybe you have very, very unique breeds of dogs, and maybe you don't have enough samples for each of those classes. You just don't have a good class balance there. You might want to merge them into some higher level class and retrain your model with that better hierarchy. And similarly, label agreement and then tools like CleanLab and Galileo kind of help surface these really, really quickly. So these are sort of the high level ways to think about how you would go about handling model problems, or even just inspecting your model generally, even if you don't think that there are problems, with a very data-centric approach in mind, looking at the data, understanding where your data falls short, what you do and don't have. And for more details on those specific issues, the 4 that I laid out, and kind of more technical and in-depth explanations of why they happen and how to fix them, Nikita, who's one of the other founding engineers at Galileo, and I work really close together at Galileo, and he writes fantastic things about this topic in particular. Here's a blog that we can share in the chat. Really recommend people read through that. It's incredibly helpful. And he's given a talk about those 4 components in much more detail. And if I have that, I will share that as well. Cool. So we've talked about kind of high level what some approaches to data-centric development are. And so I want to kind of walk through what this might look like in practice. If you have some text data, maybe you have a label, but maybe you don't even have labels, you just have samples, and you're trying to categorize them or label them really quickly, and then go build a model on them. Kind of what would that look like? So I'm going to walk through 3 different things here, one really quick workflow, and then I'm going to walk through an end-to-end labeling workflow. So the images that I showed in the beginning of that data set that had an 83 F1 score, but had those garbage samples and were really problematic, is actually from a real data set. This is from the news group's data set. We ran it through Galileo, and we trained a model, and we found those samples that were actually problematic. So you can see those in the embeddings. They're right here. So those were real samples that we found, and they were all kind of empty. And so this is obviously a very simple and quick example, but I actually did this to get the slide that I showed, and I just selected these, and I went to our data set, and I changed the label, and I added a new label called garbage, and I just kind of did that, set the label, and then went into our system, grabbed this data, kind of grabbed it as a pandas data frame, and then retrained a model really quickly just to see what would happen. And if you look across the training set, the validation set, and the test set, I did this for all 3. I came over here with a garbage label, and you can see both in the data set, the embeddings for those are right here, and the model does very well with them. Like it just perfectly labeled them, obviously, because they're all kind of the same empty samples. But what it also did, which was pretty cool, is that it found other garbage samples and surface them, even though I missed them in the data set. So I kind of went back in here, and I found another place where, if you look at these embeddings, they're colored by the label. There's a lot of agreement across a lot of these clusters, but right here in the middle, there wasn't. And so I kind of just went in and inspected these quickly and saw again that the model's doing much worse. And what's kind of cool here is that the model actually predicts garbage pretty often here, and it gets them right when it is garbage. So if you take these and you filter for those garbage samples, you'll see a lot of them like fully just are complete garbage. And so what I did is you can select these. Again, I just changed the label to the predicted label, and then retrained another model. And every time you do that, what I'm seeing here is both that the performance by class is improving and the overall performance across all the splits is improving. It's worth noting here that I am also changing the validation and the test set, which is sometimes not what you should be doing. Like the test set is typically thought to be held out. But in this case, it's kind of another example of data centricity or data focus, is that the test set shouldn't be stable or gold in this case because it was wrong, right? There are a lot of these garbage samples that did not have a label that indicated them as garbage. And so that's another case where if you're assuming that your test set is, for example, perfect, you might want to challenge that assumption and look through your test set and see if there are these same kinds of problems. In this case, there were, because it was taken from the same distribution as the training data. Cool. So that's a really quick example of a really fast workflow I did, but I wanted to showcase in case you don't have any labels, you just are kind of really fresh, you're trying to build a model. Maybe you've heard of Hugging Face, but you don't really know exactly what to do. So at Galileo, I got really lucky and I was able to work on this fun project. And it's an open source project. Anybody can use this. It's running on Streamlit, although it's certainly a Streamlit dev server. So I would recommend there's instructions at the bottom of this README to run it locally, especially if you have a GPU. But this is a tool to kind of help kick off and kickstart your data-centric process if you don't have any labels. So what it's doing here is it's a bulk labeling tool. You can select and upload any file that you want, and you'll see the same thing, but I'm going to use the demo conv intent data set to kind of walk through this example and kind of how I went about labeling a data set from scratch and then running it with Galileo and kind of fixing all of the issues that I found. So what you're seeing here is a table view, a data frame of all the samples that I just uploaded. And then what we're seeing here on the right side is these data embeddings. And what these are is they're a semantic, and you saw them in the Galileo console, but they're a semantic representation of all of your text inputs. And so when you hover over these samples, you'll see that the ones that are close together semantically are very similar, which makes, for example, classification of intent a lot easier because all the similar samples are already near each other, besides some mistakes. And so if you look around here, there's, for example, playing playlists, adding something to a playlist. Put this artist in my playlist, things like that. If you're looking over here, these are questions about like forecast of, some location. There's some gap here, and then another kind of mini cluster, for example, of like, what is the weather? And so maybe take, for example, we're trying to get really, really niche and specific in our classification. So what we might want to do is just siphon off those forecast samples. Might select those, look through here. You can kind of filter and look at forecast. All these samples, for example, have the word forecast in them. And so what you can do is register a new label. You can see the labels you've registered, and then you can come in here and select and label all those samples as forecast. You might similarly want to come into these weather samples. Oh, whoops. I don't know what just happened. Sorry. You might want to come in here and label these samples as, for example, weather, because we saw that kind of separation. You can, again, do some searching on the label, things like that. You can register a new label called weather, for example, and come in here and label those. And you can kind of continue through this process and obviously really quickly come to a very decently labeled data set, kind of with no labelers, just really fast and brute force. And then you can go about tuning these things. So I've obviously looked at this data set and I did a bunch of kind of analyzing, and I built out a data set already. But one other cool thing I'll showcase is like, you can see a lot of the word rate here. So rate this book, give this book a rating, things like that. And so you might want to search for the word rate, for example, and maybe you think, okay, you can just surface all these as a rating. And that might be a pretty reasonable thing to do. You might want to review all these samples, and then what you'll find if you pass this data through CleanLab or Galileo, for example, you've mislabeled a bunch of samples because these all say which countries are temperate, or will it be temperate in this location, has the word rate in it. Just kind of like a fun example of an easy way to mislabel data using these kinds of techniques. But nonetheless, you might want to select some of these samples. These, I think, are ratings of, oh, maybe they're empty. Need to hear a song. Maybe these are, playing some song on Spotify, something like that. And you can continue through this process and just label your entire data set. And then once it's all labeled, you can kind of export it, and you just have a CSV file of all of the samples that you've labeled. And then you can train a model really quickly and then find some issues with it. So that would be the first step in a workflow. I would upload my data, label the points that I thought were important, and then I would train a model. And so then the next question becomes, well, how do you kind of train a model really quickly and kind of get these insights? So one of the pieces that I was talking about in the slides was that if you work under this assumption that models today have gotten so powerful that if you have a data set that is reasonable to the problem you're trying to solve, a model will probably be able to learn from it and will probably be able to fit to it. And so at Galileo, we tried to kind of envision that and encapsulate that into a really easy to use function. So if you have data, it's been labeled, but you don't yet have a model, you don't really even necessarily want a model, you can just pass it through a function that we have called auto, and it'll leverage Hugging Face and automatically train a model, and then train that model and log all the data and analyze it within Galileo. So you can, all I did was I took that data set, I uploaded it in Colab because there's a GPU. I called auto and just passed in the path to my CSV file. You can pass in a bunch of different formats of your data, and it's all in the docs, but I passed in the CSV file. It kind of parsed it and set it up with training and validation data for me, trained a full model, passed it through, and then I kind of started to analyze it within the Galileo console. So this was the conv intent data set that I bulk labeled. I didn't use the built-in labels. And so I started kind of looking for insights within this. So I did kind of all the things that I was talking about in the slides. And what's nice is that actually a lot of these things were surfaced for me within Galileo. So for example, one of the ones that I thought was really cool is that this first one right here, samples with values Spanish and unknown in the language. So Galileo tries to detect the language of every sample. And it said that these samples are performing a lot more poorly, and kind of want to figure out why that is. So you click on show and you look at this data, and you can kind of see where it sits. You can hide kind of all the other points, but to get an understanding, it's sitting between these two clusters, which were the play music and the add to playlist cluster. And so you might be thinking, okay, like that kind of makes sense. Those two labels are pretty similar, but they both have pretty robust numbers of samples. You can just see by these clusters here. There are a lot of examples of both of those. I wonder kind of why the model is making that mistake. And if you look into these samples, what's really wild is that all of the songs or the artists have names that are not English, which is kind of wild. The model is just not performing well in differentiating these two classes when the artist or the playlist or the song is not an English word. And so maybe you need to switch the model that you're using that encapsulates more languages, or maybe you just need to add a lot more samples of songs that are not in these languages to give your model a better representation of this kind of data, so you can go about kind of handling that. So you might want to delete it, for example, if you don't think these will show up in production. But if they do, you obviously need to deal with that by adding more samples from these data sets. So that's like one really quick example of an insight that we found. Another one that I found that was pretty cool here is that the class find book has a low F1 score and a relatively low class distribution. So I wanted to look at that and see what was going on. It's doing really poorly. And if I look at the data set view, or at the embeddings view here, you can see there's like very few samples. There really just might not be enough of these samples. And so you might want to delete these samples. You might want to merge these samples and kind of push them into another class. Or if you think that this is important, you're going to need to grab a lot more samples from this class, because you can even see right here, way fewer samples are in this class than a lot of your other, right here, a lot of your other classes. So another cool insight that I was looking for when I was looking at this data set were mislabeled samples. So we were talking about finding samples that might just be labeled incorrectly. And one of the things I wanted to do here was see, of my mislabeled samples, what is the most commonly confused classes? And so I looked at it and I saw there was play music and add to playlist. again, those are pretty similar. But the model actually was predicting correctly here. The model was predicting add to playlist, but the ground truth was play music because I obviously messed up when I was selecting those points. And so what I was personally curious about was if the same was true of the other way, the samples where it was add to playlist, but the prediction was play music. So I kind of came in here, added those filters, and I took some time and read through these, and they all pretty much seemed to be correct from the model's perspective. The model was predicting them right, and we were incorrectly penalizing them. So I came in, I changed the label to predicted, and I set that label, and I added it to our cart for editing it and grabbing a new data set. And so as I go through these, I'm building up this edits cart of all of the samples that I'm fixing, all of the samples that I either were wrong from a text perspective or wrong from a labeling perspective, or were overlapping with another class, or missing a label, for example. Another one that I did was looking at, for example, the word forecast. So I was searching for the word forecast, but I wanted to see where the ground truth was actually weather, because we were being very kind of picky there, specifically the word forecast. And so again, another really simple case, change that label, set it to the prediction, or just set it equal to weather, or to forecast right here. Add that to the cart and kind of continue along this process. And yeah, so I kind of walked through all of these samples, found all of these points of biases or points of imbalance, or kind of just problematic points at all, using a lot of actually the insights that I got automatically, which I wasn't necessarily expecting. And then all I did was I came in here, I found all the samples, made sure that the edits kind of looked like what I wanted them to look like. And then I grabbed my data frame, came back, copied this code, and came back to the notebook and just grabbed it again, grabbed my edited data frame from that code I got, and then I just kicked off a new model run, and you can retrain. And the idea generally is that you continue with this process, and as you fix the really low-hanging fruit of problems, the harder to find problems and the more tricky ones will begin to surface, because all of the easy ones, which are kind of right in your face and easy to find, are fixed. And so as you iterate through this process, you continuously get a better data set. And with that, you continuously build a more robust model. And the idea here is you can do this process over and over again before you even pull out your own model. And by the time you want to grab a custom model, if you even do, the data set will be really well formed. You'll know all of the hidden pieces that you've missed, all the gaps and all the holes, and you can kind of work forward knowing that your model will be more robust because your data is better represented of that problem. Cool. So that was the main piece of the demo. And besides that bulk labeling tool being open source, Galileo is free. So all the things I did in this demo are completely achievable and free to do. You go to the website, you sign up for a free account. Everything I did was just using a free account from our cloud offering. So yeah, I encourage everybody to both read the blog that I shared as well as try this for yourself.